Hi and welcome. I'm trying to learn biographyology. Today, all the Roemer, and after we've done with, we're going to do body central training. And if you participate in the body central training, then is that at your own risk. Now, we have just a dictionary entrance to all the Roemer. All the Roemer, he lived from 1644 until 710. And he was a Danish astronomer who in 1676 first measured the speed of light. Okay, Danish. That means from Denmark, and that is in Europe, and it's north of Germany. So there's France and then there's Germany, and directly on top of Germany is Denmark. And also in the 17th century, it was there. It looked. I think the borders were a little different, but it was there. So, Ole Roemer was from Denmark and he lived in the 17th century. And in 1676 was he first measuring the speed of light. Observing the times of eclipse of Jupiter's moons, Roemer found that they differed from the predicted times depending on the That is really amazing. I'm reading two words before I say it and I understand it already. Observing the times of eclipses of Jupiter's moons, Roemer found that they differed from the predicted times depending on the distance between Jupiter and the Earth. Now, Jupiter and Earth are not always at the same distance to each other. Maybe you heard it with Mars. Maybe you heard someone saying that it takes a different time to go to Mars. It can be a few months or more months depending on where Mars and Earth are now in the universe. The Moon and Earth are always the same distance. The Moon is always turning around the Earth, always the same distance. Also, the Earth has almost always the same distance to the Sun. It differs 2 seconds at light speed, but it's almost the same size, almost the same distance of Earth to the Sun, and the Moon has always the same distance to the Earth. But Jupiter is another planet. So there is Mercury, Venus, Mars, and then Jupiter, Uranus, Neptune, and there's Saturn, Jupiter, Uranus, Neptune. Jupiter, Saturn, Uranus, Neptune. Now, and there's no Jupiter. It doesn't matter now. And they are not always the same distance, Earth to Jupiter. They are basically independent. The Earth moves in 1 year around the Sun. And I think Mars is faster. I think Mars was 200 days. Maybe there are 400, whatever. It's differently already for Mars and Earth. And for Jupiter, it's again differently. So they're not moving all in the same distance around the Earth, around the Sun. They're not the planets Jupiter and Earth just going like that always around the Sun, but the Earth is, I think, faster than Jupiter. Would make sense. The Earth goes faster around than Jupiter. So if we're starting at the same place here as the Sun, then the Earth is faster around. And now, Earth and Jupiter are way more apart as when we were at the start. So if you now predict the time when the eclipse is visible on the Jupiter's moons, Jupiter has moons, just like Earth has a moon, has Jupiter, multiple of them. And they can have an eclipse, and that can happen if, I don't know how it works now with Jupiter, let's just say the Earth moves in front of the Sun, and now one of these moons is in the shadow of the Earth, or somehow, some of these, one moon is now for some reason in the shadow. Like the moon eclipse. But moon eclipse, where the Earth you are here on Earth, and you see the moon peacefully here, and you can see the moon with the sun shining onto it, but then the Earth moves basically in front, or the moon moves around, I think it goes the other way around, in front, and now the Earth is making a shadow to the moon, something like that. It's now in the sun, but then you stand here, you see the moon, and then it comes into the shadow. And now you see the moon in shadow, until it comes out again. Now that is a moon eclipse, and you see the same then on Jupiter. They are also, for some reason, I don't know how it works on Jupiter, the moon suddenly in the shadow. And you see the shadow moving over it, and you can calculate it, because the Earth goes always at 365.25 days around the Sun, always the same. And you also know when the moon comes. The moon comes every 28 days around the Sun. And the same happens to Jupiter. Jupiter goes, let's just say every 3 years, I have no idea, every 3 Earth years around the Sun. And Jupiter has been exactly on that day its eclipse. You can all calculate it. And now when there was now all the Roemer or some other people who calculated tomorrow at 11 o'clock, that moon will have an eclipse. When you can now look with a telescope and see, yes, at 11 o'clock there's an eclipse. But now you can see it at 11 o'clock when Earth and Jupiter are for some reason quite close together. But now say 2 years later, you see another eclipse. But now Jupiter is here and the Earth is just right now here. And now, that happens not at 11 o'clock. It happens 1 second later, or whatever. And the explanation for it is that the light had needed time to travel now from Jupiter longer to see what happens at Jupiter when it was closer. So when it was close, you could see directly, or just a tenth of a second later, that it happened. The light needs a bit of time to travel that distance. But now when you're further away, that light needs longer to travel. And you see it 1-2 seconds delayed. And that was what he did. Let's get on by explaining it a little bit, I think. I've saw a few numbers. Roemer surmised that the difference was caused by the time light took to travel between Jupiter and the Earth, and in this way he calculated the speed of light as being 225,000 kilometers per second. About 3/4 its true value of 299.793 kilometers per second. Okay, he did exactly that, and he thought the only explanation for that is it takes longer when we're here to see what happens here. We need 2-3 seconds later. The explanation for it takes longer until they see it. I think now, basically, if someone asks how came he up with that idea, I would just say maybe he knew about sound, that he knew if you stand close to another person, you hear them directly. Like, make it differently if you hear someone making a sound, kicking a football. You can see it maybe sometimes on a football field. If you're 100 meters away, you see the person kicking and you hear it then half a second later. Maybe you can try to see it actually. But if someone fires a shot or someone makes a clap or whatever, something loud, and you're 100 meters far away when you see it half a second almost later. Or you can do it also with other things, with sound. You can have a horn and you can be a kilometer away. Someone plays that horn or makes a big movement and you see that movement immediately because the light is basically almost there. And you see that person making the movement to clap, but you hear it over kicking, but you hear it then a second later. And I think that would be an explanation how he came up with that idea that he knew that sound needs some time to travel. Sound moves, I don't know, 1,000 kilometers per second. No, it doesn't make sense per hour. It needs half a second for 150 meters. And maybe he knew it, and then he thought, why should not also light need some time to travel? I mean, if you see it coming in through a window, it's basically, if you open the door of a window and when the sun is there, why should you not think it comes in? It's immediately there for the eye, but it's the way as it comes in, and that's also how the sayings are going, the light comes in. So basically his idea was, the light needs time to travel. And I calculated we are that far apart, that are, I don't know, 500,000 kilometers, it must be way more. 5 million, I don't know how far, 5 billion kilometers, whatever. And he said when we're seeing it 8 seconds later, that means that light, he knew for some reason we are 5 billion kilometers apart, and he said when the light is 8 seconds later than it should be, as if you're next time closer, now the light travels with 225,000 kilometers per second. And he said when light travels with a speed of 225,000 kilometers per second. And he was pretty close, it actually 300,000. So it was 220,000 to 300,000. That is what is written here, and we have information. Otto Roemer, Danish astronomer, lived in the 17th century, and in 1676 he observed the eclipses on the Jupiter's moon. And he found that they differed from the predicted times depending on how close Jupiter and Earth are. He calculated the speed to 220,000 kilometers per second, that are actually 300,000, but he had the idea and he calculated that pretty precisely. I'm going to start the camera and try to say that. Otto Roemer. He lived in the 17th century and he was from Denmark. And he was looking in the sky in the stars. He was an astronomer. And now in the year 1676 he discovered that light travels and he calculated the time it needs to travel and the speed of light. He knew the time when it was predicted that the moons of Jupiter, another planet, so there's the Sun, there's the Earth and there's Jupiter, that the moons of Jupiter has also moons just like the Earth has a moon. have eclipses, so that one planet moves in front of the other one, so that there is no a shadow on one of the moons. And they can be predicted. The people know it happens tomorrow at 12 o'clock, 11 o'clock, or whatever. But he found out that there is a delay. And that amount of delay, how when the eclipse was seen on Earth, what happened on the moon of Jupiter, were together with the time, the place where Jupiter and Earth were. So when they're close to each other, then you can see it almost directly what happens at the moon with the eclipse at Jupiter. But now, when Jupiter and Earth are traveling around the Sun, they don't do it together. One planet is faster and Jupiter is there or whatever, and now we're further apart. So we are close, and now you see it almost immediately, what happens with the eclipse, and then you see it a few months or a few years later, they are further apart, and now it happens way longer until you see it. It happens delayed. And he found out this delaying has always to do with how much apart they are, and he said then the reason for that must be the speed which light travels with. So just like sound comes a bit delayed, half a second for 150 meters, he even thought light has also delayed, and he measured and he calculated, and he came to the idea that when we're close, it happens that and that time later, and when we're far away, it happens that and that time later. So light travels, he said then, 225,000 kilometers per second. He was close, it are 300,000 kilometers per second. And that is according to page 66 of Structures of the Universe of the Reader's Digest Library of Modern Knowledge, book part 1, written by Ian Ridpath and John R. Shakeshat. I'm going to stop the camera. And that was the biographyology part. If you were here for biographyology, you can go directly to the next part of biographyology or space science, if you want to see that. If you stay here and participate in the body central training, and we're having the legs standing around hip width apart. We're going a bit down into the knees, and now flex the leg muscles and press the legs together. And now straighten one leg, slowly, straighten it. Completely straighten, press together the whole time, and straighten. Now bend again the leg, press together, flex the legs, and straighten the other leg. Press together, flex, and bend again. Similar exercise, wider apart, again down into the knees. Flex again the leg muscles and press them together. And now bend again one leg. Straighten completely, press together, flex. And bend it again, press together, flex. Bend the other leg, straighten the other leg. Flex, press together, and bend the knee again. Press together, flex, a little bit, and up. And the other way around. Legs good standing and press to the outside. And back into the middle. And now one leg up. Press from the top against the knee. Right angle of the leg, flex foot. Even aligned hips, taller with the back, little bend in the elbow. Now press forward, middle part, inside. And now press with the knee up and to the side, up to the side. Other knee, press on top. And from inside. Press top up to the side. And the heavy swing go, knee up, press from the outside, and up slowly. And cross again. And other leg, press from the outside, and up slowly. Cross again. And now 3 exercises on the ground. So first the side leg, on the elbow to the side. And if you like and can, now one leg up. And now on the long arm, first standing. Then one arm out and leg up, and bring knee and elbow a few times together. Now over to the other side. First on the elbow. Now if you like and can, one leg up. And the same on the long arm. First a bit standing. Arm out, leg up, and now elbow and knee together. And we're coming up again. Let's follow the path of your breathing in, going down. And out. In and cross the legs. And breathe again out. Great pose for body center training. I thank you very much, and until next time.